This chapter will focus on the chemistry of aldehydes and ketones, primarily the nucleophilic addition reaction. Ketones are a functional group that contain a carbonyl, a carbon-oxygen double bond surrounded by two alkyl groups on the carbon. An example is acetone. Acetone has two methyl groups surrounding the carbonyl. Acetone is the primary ingredient in nail polish remover. Aldehydes, on the other hand, will have an alkyl group and a hydrogen bound to the carbon of the carbonyl. An example is benzaldehyde, cinnamaldehyde, as shown on this slide. Camphor is another example of the ketone. Aldehydes and ketones are found widely in nature. A few examples shown here. The ketone on the left is the active form of vitamin B, and hydrocortisone is a ketone that is used to treat inflammation and allergic reactions. Aldehydes and ketones are also products of metabolism and biosynthesis. Very often, alcohols will be oxidized into aldehydes and ketones through these pathways. And ketones are hydrogen bond acceptors due to the oxygen on the carbonyl. That oxygen can accept a hydrogen bond from a protic solvent or other compounds. As shown here, water will donate a hydrogen bond to this oxygen. Aldehydes and ketones can also interact with each other through London forces and, more importantly, through dipole-dipole interactions. In dipole-dipole interactions, the negatively charged oxygen of one carbonyl will align next to the positively charged carbon of another carbonyl. Due to the dipole-dipole interactions of aldehydes and ketones, they tend to have higher boiling points and water solubility than alkanes, but not as high as alcohols. Here is a few examples. An alkane, in this case butane, has a boiling point of around 0, very low water solubility. An aldehyde and a ketone that of similar molecular weight will have a higher boiling point, higher water solubility, and then an alcohol, in this case propanol, has a much higher boiling point and water solubility. Aldehydes will be named with the suffix -al. The parent chain must contain the carbonyl functional group, and generally, unless there's a higher priority functional group in naming, the carbonyl will typically be carbon 1. Here's a few examples to illustrate these rules. The first example is heptanal. It has 7 carbons. The carbonyl is, of course, at the beginning of a chain, since an aldehyde, by definition, will be always on the edge of a molecule. So the carbon that contains the aldehyde will be carbon 1, and then we're going to number from right to left. On the next example on the right, we have a 5-carbon aldehyde. So this would be named as pend. It has also an alkene on carbon 2, so 2-ene. And then we have the suffix -al to indicate that we have an aldehyde. Notice that we don't number generally the location of the aldehyde. You could, it wouldn't be wrong, but we don't need to, since the aldehyde is by definition at the beginning of a chain. It is always going to be carbon 1. We also have a methyl substituent on carbon 3, so we add 3-methyl in front of the name. And then lastly, we look for any stereochemistry. In this case, we have a double bond that has E stereochemistry. You can tell that by the fact that the aldehyde is going in this direction, and then between the methyl and the ethyl group, the ethyl has a higher priority, and that one is going in the opposite direction as the aldehyde was. So therefore, we name this or give this E stereochemistry. In the last example here, we have a 6-carbon aldehyde. So this would be named as a hexanal. Once again, we don't really say where the location is since the aldehyde is assumed to be on carbon 1. We do have two substituents, a methyl group on carbon 4 and a hydroxy group on carbon 5. So we alphabetize those two substituents. So it's 5-hydroxy, 4-methyl. Lastly, we look for stereochemistry around carbon 5. There is R stereochemistry. So oxygen is highest priority. This chain is second priority, and the methyl group is the last priority. So going in a clockwise fashion, we are going to we're going to have R stereochemistry. And then on carbon 4, we have a methyl substituent that has stereochemistry as well, which is also R. In this case, this carbon here, carbon labeled as 5, is the highest priority. Carbon 3 is the second highest, and the methyl is the third highest. So we would go from 5 to 3, again going on a clockwise direction, and therefore this is R. Like many functional groups, aldehydes are sometimes named through their common names. For example, formaldehyde has a single carbon. It is the simplest aldehyde we have. Acetaldehyde has a methyl group along with the aldehyde, and then benzaldehyde has a benzene ring next to the aldehyde. Note that formaldehyde has been used in preserving biological specimens. So 30% solution of formaldehyde in water is known as formalin, which is an excellent biological preservative. It has been replaced in many cases by other preservatives, such as a 5% solution of ethanol with added antimicrobials. Naming ketones, we want to use the suffix "-one". If we have more than one ketone, we will use the suffix dione, trione if we have 3, and so on. As always, we want to indicate the location of the carbonyl with the lowest possible number. So we would start counting from the side that is closest to the carbonyl. And we have to make sure that the parent chain in naming the compound contains the carbonyl. As an example, we have here on the top left a ketone that has 6 carbons, and if we count from the left, the ketone will be on carbon 3 as opposed to counting from the right where it would be on carbon 4. As a result, we number this as a 3-hexanone, or if we use the newer IUPAC system, hexane 3-one would be the name for this ketone. In the next example, we have both an alkene and a ketone. The ketone, it would be the highest priority group or functional group here. So we would number this from right to left, meaning the ketone will be on carbon 2, the alkene is on carbon 4. So we name this as hex 4-ene-2-one. On the next one, we have 2 ketones, and there are 6 total carbons. So this is named as hexane 2,4-dione. The next example has has 6 carbons, and it has a carbonyl on the second carbon from the right side. So we would name this as hexane 2-one. It has 2 substituents, an amino group on carbon 4 and a nitro group on carbon 5. If we alphabetize those groups, we would have on carbon 4 an amino group, and then 5 nitro, hexane-2-one. And then lastly, we add the stereochemistry. The amino group around carbon 4 gives this R stereochemistry. The nitro group on carbon 5 has or gives this carbon S stereochemistry. Notice that the amino group is a new substituent that we haven't covered before. So try to add that to your substituent names. This last example here has a cyclopentanone parent name. So there's 5 carbons in the ring. There's a ketone on carbon 1. So it's named as cyclopentanone. Sometimes we drop this 1 since in a ring, typically you don't need to give the location of the ketones. This is going to be assumed to be on carbon 1. And so we could just have cyclopentanone without the number. We also have a substituent on carbon 3. So if the ketone is carbon 1, the hydroxy group is on carbon 3, going from the top to the right side. And so this would be named as 3-hydroxy cyclopentanone. And then lastly, we have S stereochemistry around carbon 3. So that is added to the name. To remind you, this is S stereochemistry since on carbon 3 there's an oxygen, which is the highest priority group, followed by carbon 2 since it's closest to this carbonyl, and then carbon 4 is the third priority. So we would go from the oxygen, carbon 2, carbon 4. So we're going counterclockwise, which means this is S stereochemistry. If you have an example of a ketone or an aldehyde in a molecule that has another functional group with a higher priority, we can use the substituent name oxo for aldehydes and ketones to indicate that they're on the molecule. In fact, ketones are a lower priority group than aldehydes. So if we have both a ketone and an aldehyde in the same molecule, we can indicate the ketone as a substituent with oxo. In this first example, we have a 6-carbon aldehyde that also has a ketone. So the aldehyde is, of course, on carbon 1. So we would name this as hexanal. And then we have the ketone on carbon 3. So this would be named as 3-oxohexanal. Notice again, we don't need to indicate that the aldehyde is on carbon 1, since by definition, aldehydes will always be on carbon 1. In the next example, we have again an aldehyde and a ketone. And so we would name, and we have also 6 carbons in the parent chain. So this is named as 5-oxohexanal, since the ketone in this case is on carbon 5. We have a substituent on carbon 3. So we add that substituent in the front of the name, so 3-bromo. And then lastly, we have the S stereochemistry of carbon 3. So we can confirm that by looking at the substituents around it. Bromine would be the highest priority group. Then we have this carbon 2, carbon 4. If we start counting or start moving away from the chiral center, we can determine which group has higher priority. So if we move on to the next carbon, we're comparing a carbon to another carbon, carbon 5. And then if we move on to the next set of substituents, we have a double bond to an oxygen. We have a double bond to an oxygen on this side. There's a hydrogen and there's a carbon. So carbon 5 has the highest priority, since as far as determining stereochemistry, because of this methyl group versus this hydrogen on this side. So carbon 4 has the highest priority over carbon 2. So if we go from the bromine to carbon 4 to carbon 2, we're going counterclockwise. So this is S stereochemistry around carbon 3. There's a few common names that you should be familiar with for ketones. Acetone, which is a common organic solvent we're going to use often in organic labs for SN2 reactions, for example, since they're aprotic polar solvents. It is also used for a lot of other industrial uses like removing paint, among other things. Acetophenone is this ketone here with a methyl group and a phenyl ring, and then benzophenone has two benzene rings attached to the carbonyl. This question here asks us to draw the structure of 3-methyl-butanol. So I encourage you to try that out before looking at the answer on the next slide. 3-methyl-butanol is a very simple aldehyde. Based on the name, you can tell that it is going to have 4 carbons. So but means 4 carbons, and it's going to be an aldehyde. So we want to draw 4 carbons and with an aldehyde on at the beginning or the end, whichever way you want to look at it, of the chain. And then on the third carbon, so if the aldehyde carbon is carbon 1, on the third carbon we are going to add a methyl group to complete the name. In covering the reactions to prepare aldehydes and ketones, let's begin by reviewing some of the reactions we should be familiar with already. For example, one of the ways we can make an aldehyde or a ketone is by oxidizing an alcohol. If we oxidize a secondary alcohol, as shown in this example, with some sort of chromic acid, so we can use chromium trioxide or we can use sodium dichromate, mixed in with sulfuric acid and water will make chromic acid. That will lead to oxidizing a secondary alcohol into a ketone. We can do the same thing with PCC as well. When it comes to aldehydes, one of the most common ways to make aldehydes is by oxidizing primary alcohols. We would typically use PCC or pyridinium chlorochromate to do this oxidation. You might recall that if we try the same thing with chromic acid, we would typically, instead of an aldehyde, instead obtain a carboxylic acid. There's a molecule in biological systems that is called NAD+. This is a natural oxidant that will often be used by cells to oxidize alcohols into ketones and aldehydes. We can use the reduced version of this coenzyme called NADH as a reductant, which will do the reverse reaction, and it'll take an aldehyde or a ketone and convert it into an alcohol. The Krebs cycle, or the citric acid cycle, is a very important metabolism pathway in eukaryotic cells that converts pyruvate into CO2, ATP, NADH, amino acids, lipids, and nucleotides, among other molecules. Pyruvate is in itself a breakdown product of glucose. Here in this cycle, we can see several occasions where NAD+ and NADH are involved in oxidation and reduction reactions. For example, in this last step here, we have malonate being oxidized. So in particular, this alcohol here on the second carbon from the bottom is oxidized into a ketone through NAD+. Method to make aldehydes and ketones is through a reaction we saw previously, the hydroboration of alkynes. If we have a terminal alkyne and we add borane, hydrogen peroxide, and base, we can oxidize the alkyne into an aldehyde. Notice the aldehyde will have the same number of carbons. So here to begin with, we have 1, 2, 3, 4, and 5 carbons. And the product will have also 5 carbons. You can think of this oxidation as adding an oxygen or an alcohol at the terminal carbon. We typically expect this from hydroboration. We typically will have a anti-Markovnikov addition that will give us a double bond and an alcohol, which is called an enol, and that intermediate always is converted very rapidly into an aldehyde. If we have a terminal alkyne and again we do a hydroboration, we'll end up with an aldehyde. However, when we use an internal alkyne and we do a hydroboration, we'll always get a mixture of two ketones, since it is just as likely that we'll add the carbonyl to the right carbon or the left carbon when there are two similarly sized alkyl groups on each end of the alkyne. So in about approximately 50-50 percent, we'll obtain these two ketones. Also look at the mechanism of this reaction. It starts off with the alkyne attacking the boron. So when you have a boron with 3 groups attached to it, that boron only has 6 valence shell electrons around it, so 2 from each bond. And as most atoms, it prefers to have 8 valence shell electrons, so it is a great Lewis acid and can accept electrons such as those from the pi bond of the alkyne. So the alkyne is a nucleophile, it will attack the electrophilic boron. Once that addition occurs, that puts a formal negative charge on the boron, and that negative charge will actually spread out to the 3 hydrogens, since hydrogen is more electronegative than boron. So that makes these hydrogens sort of like a hydride and nucleophilic as a result. So one of these hydrogens will be added to the developing partial positive charge on this carbon, on the internal carbon of the alkyne. So you can think of that carbon as sort of becoming a carbocation. And so as a result of this addition, the boron will add to the least substituted carbon, and the hydrogen from the borane will add to the more substituted carbon. They're generally added from the same side, so this is a syn addition. The boron typically will end up on the least substituted carbon since there's less sterics there, and BH2 is a bigger group. And the hydrogen will typically be added to the more substituted carbon of the alkyne, since that is where we're going to have more of a partial positive charge compared to the any charge that would develop here. The next step would be a oxidation of this BH2 group and conversion into an alcohol. This is not a mechanism we typically cover. The result of this next step is an enol, which you can see highlighted here in sort of a pinkish color. We have an alcohol on the same carbon as this double bond. So that is what we refer to as enols, which we'll cover in much more detail later on. But enols are always in equilibrium with a carbonyl. They're called tautomers of each other, and they undergo a tautomerization. The way you can think about enols and keto forms are essentially that these are rapidly interconverting constitutional isomers. So if we count the number of atoms in these two compounds, you'll notice that they are exactly the same type and number. So for example, there's 1 oxygen. There are 3 carbons in both. And if you count the hydrogens, you'll find that they're the same as well. So this is always true between an eno and a keto form. They are constitutional isomers of each other by definition. And they're always rapidly interconverting, and so that's what makes them tautomers. There are other examples of tautomers, which we'll discuss later in the course, but this is probably the most common type, an eno and a keto form. Notice the equilibrium is always favored towards the keto form in not always, but in most cases. And so whenever we get in a mechanism an eno form, it usually interconverts into the keto form. Another reaction that we covered previously is the conversion of an alkyne into a ketone through oxymercuration. So if we take a terminal alkyne and we add mercury sulfate, sulfuric acid, and water, we can obtain a ketone. Notice the ketone or the carbonyl will always be added to the more substituted carbon of the alkyne. So in this terminal alkyne, it will be the second carbon. However, if we start with an internal alkyne, there is not much of a difference between the carbon on the right and the carbon on the left, even if the two have different size alkyl groups. For the most part, they won't be enough of a difference. And as a result of oxymercuration, we'll end up with two different ketones, resulting from adding the carbonyl on on the left side or the right side. So in this case, there's actually no carbon that is more substituted per se, and so we end up with these two ketones. Notice this is very similar to the hydroboration of internal alkynes. We end up with two ketones. With terminal alkynes, whether it's through oxymercuration or hydroboration, you can get a single carbonyl. In the case of hydroboration, we end up with an aldehyde. In the case of oxymercuration, we'd end up with a ketone. Here's another example of oxymercuration of a terminal alkyne. As you can see by this example, we have a 3-carbon alkyne, so we end up with a 3-carbon ketone. The ketone will be added on the second carbon, and so we end up with this ketone acetone, to be exact, on the right side. Here's a look at the mechanism for this reaction, covering some parts, at least the most important parts of the mechanism. The reaction starts by the nucleophilic alkyne attacking the mercury. So the alkyne has pi electrons, so it's a good nucleophile. Mercury is it's going to have a partial positive charge since it's bound to sulfates. Just the fact that it's a sort of a metal also makes it electrophilic, and so it is attacked by the alkyne. At the same time, the d orbital electrons on this mercury will start to attack the developing positive charge here on this carbon, the more substituted carbon of the alkyne. And so we end up with sort of a 3-member ring, which we call a mercurium ion. We certainly ended up with these mercurium ions when we do a oxymercuration of an alkene. But in the case of an alkyne, due to the fact that we still have a double bond, that 3-member ring doesn't really want to form. So we often draw the mercurium ions sort of in this fashion, where the mercury is bound on the less substituted carbon, and then it has sort of a partial bond, to the more substituted carbon, which has a positive charge. The water will then attack the more substituted carbon where there is a large positive charge there, and we get the Markovnikov addition of water. So the alcohol, or the water, will be on the more substituted carbon of what used to be the alkyne, and then the less substituted carbon will have the mercury sulfate. We will then remove one of the hydrogens on this water molecule that just added through using another water molecule or some other base in the reaction. It will pick up that proton, put the electrons from this bond between oxygen and hydrogen, put those electrons into this oxygen to get rid of the positive charge. And so we have now an alcohol that is bound to this double bond. Then sulfuric acid and water will convert mercury sulfate into a hydrogen through a mechanism we're not going to go into. And then we finally get to this last intermediate, which we call an enol. Notice as highlighted here, we have an OH bound to a double bonded carbon. So that's what we refer to as an enol. And as we learned previously, enols are always in equilibrium with a keto form. So wherever the oxygen is bonded to, that carbon will become a double bond in the keto form. And then this double bond will become a single bond. And so we have acetone as a product from this reaction. When we cover the reactions to make alcohols, one of the reactions we talked about was the reduction of esters into primary alcohols. We can do this reaction as shown here with lithium aluminum hydride. So this involves the addition of two hydrides to this ester to make a primary alcohol. So initially, the hydride will attack the carbonyl, and then once the carbonyl is reformed by expelling this OCH3 or the methoxy group, we end up with an aldehyde intermediate. An aldehyde intermediate is reduced again with lithium aluminum hydride into this primary alcohol. If we want to stop the reduction at the aldehyde, the intermediate that we talked about in the reaction above, one way to do this is through another hydride reagent called dibol. Dibol is an acronym for diisobutyl aluminum hydride. We sometimes refer to this intermediate as dibol or dibald H. So this is a hydride reagent that is sort of specialized to reduce esters into aldehydes. As we'll see in the next slide, the mechanism first starts with the dibol binding to the carbonyl oxygen. Dibol reduction of esters typically is done at fairly low temperatures. So one of the most common temperatures that we use is negative 78 degrees Celsius. Now you might wonder why 78 degrees Celsius, negative 78 degrees Celsius. What is so special about that temperature? Well, it turns out it's not really that exact temperature makes this reaction occur. It is just that it's a practical temperature to work with, since mixing CO2 and acetone makes or gives you a solution that is exactly at that temperature. So we refer to this as a dry ice bath. So it allows us to cool reactions to close to negative 80 degrees Celsius. So that turns out to be a low temperature that we need in order to make this reaction occur. Here is one more example of an ester being reduced into the corresponding aldehyde. Notice the same two carbons in the ester will be part of the product, and then this methoxy group is expelled as a methanol byproduct. Here's a look at the mechanism of a dibol reduction of an ester using the previous example on the top. So the reaction typically starts by the carbonyl oxygen attacking the aluminum. The reason for this is we have lone pairs on this oxygen, which makes it a base, a Lewis base. Note that this oxygen also has lone pairs, so it's also a Lewis base, but this is more basic. This carbonyl oxygen is more basic, since we can use the lone pair from this oxygen to push electron density through this double bond. into this oxygen, so there's more of a partial negative charge on this oxygen. And so carbonyl oxygens generally tend to be more basic, more nucleophilic than other sp3 oxygens near it, such as the one that we see here from this ester. The reason why this carbonyl attacks the aluminum is because aluminum is a Lewis acid. So anytime you have aluminum or boron with three groups surrounding it, we're going to have a Lewis acid. So uh, if an aluminum atom has three groups, that means that that aluminum has 6 valence shell electrons around the aluminum. And so it wants to pick up 2 more electrons to have a full octet. So we can do that by accepting a lone pair from this oxygen to make this intermediate here, which is a Lewis acid base adduct. The oxygen will now have a positive charge. The aluminum will have a formal negative charge. They're bound to each other. That now activates this hydrogen on the diball to be a hydride reagent. So the formal negative charge on the aluminum means we're going to transfer some of that negative charge and most of it to this hydrogen, since hydrogen is more electronegative than aluminum. That places a partial negative charge on this hydrogen. It allows it to behave like a hydride, and so it's going to attack the carbon of the carbonyl of this ester. So there is now a partial positive charge on this carbon because there's a formal charge on the oxygen, and oxygen is more electronegative than carbon, so we prefer to have the positive charge on the carbon. So even though formally there's a positive charge on the oxygen, this molecule, this intermediate, behaves as if we had the charge on the carbon. And the hydride will attack the carbon and then break the double bond to give us our next intermediate. Now notice diball is slightly different than other hydride reagents we talked about, like lithium and aluminum hydride and sodium borohydride. So those reagents, in the case of lithium and aluminum hydride, had an aluminum atom that had four hydrogens around it. So this is the structure of lithium aluminum hydride. It has aluminum in the middle. It has four hydrogens around it, and then there's a lithium somewhere around it with a positive charge. This aluminum, because it has four groups around it, has a formal negative charge. Diball, to begin with, as shown here in the beginning, only has three groups, so there is no formal negative charge on this aluminum. Once it binds to the ester, it picks up that negative charge. So now this starts to look more like lithium aluminum hydride. This is already set up to be a hydride reagent from the beginning. Diball, unlike lithium aluminum hydride, has to first bind to the carbonyl oxygen before it behaves like a hydride reagent. So that's the part of the reason why these two reagents behave differently. Now, under the low temperatures that we're using for the reaction, we're going to get this intermediate that is going to be very stable at that temperature. So the aluminum, after the hydride has been delivered, will be bound to both oxygens and sort of hold that intermediate in place so that it doesn't break down and eliminate the leaving group. Once we start to warm up the reaction, in other words, once we're done with the reaction, we now start to break down this intermediate. So by allowing this intermediate to now warm up with aqueous acid, we can now eliminate the leaving group, the methoxy group, and end up with an aldehyde and also methanol byproduct. So as a result, diball will only reduce an ester into an aldehyde, while if we did it with lithium aluminum hydride at room temperature, we typically obtain an alcohol in that case because of the continuing reduction of this aldehyde with lithium monohydrate. Another method to make aldehydes and ketones, specifically ketones, is by using a reagent called the Gilman reagent. Sometimes we call it cuprase or diorgano copper reagents or lithium dialkyl copper reagents. So there are many names for it. And before we get into the reactions of using a Gilman reagent to make a ketone, let's first talk about how these Gilman reagents are made. So this is a reaction that is typically covered in Organic Chemistry 1, but let's review the reaction. If we take an organolithium, two equivalents of an organolithium, and we add copper iodide, we can make a Gilman reagent, which is lithium next to a copper that has two alkyl groups. A byproduct of this reaction is lithium iodide. One of the reactions that Gilman reagents do is they transfer an alkyl group to certain alkyl halides. So for example, this vinyl alkyl halide, the bromine will be replaced by a methyl group from the Gilman reagent to give us this product here. We'll also obtain a byproduct of copper or methyl copper as well as lithium bromide. Another reaction that is very similar to what we saw in the previous slide is that we can, instead of an alkyl halide or a vinyl halide, we can start with a acid chloride and replace the halogen with the alkyl group on the Gilman reagent. So here we see an example of a acid chloride reacting with this Gilman reagent, and an ethyl group will be replacing the chlorine. In this next example, we have a propyl group on the Gilman reagent, and that will replace the acid chloride, in particular the chloride from the reactant. Notice that Gilman reagents do not add to any other carbonyls, so they will not add to an ester, for example, or an amide or carboxylic acid to give us ketones or any other product for that matter. One of the most common reactions for aldehydes and ketones is nucleophilic addition reactions. Now, there are two pathways for nucleophilic addition reaction depending on the nucleophile. The most common pathway is where a nucleophile attacks the carbonyl. That leads to breaking the double bond of the carbonyl, placing a negative charge on the oxygen, and this gives us a tetrahedral intermediate. The tetrahedral intermediate is then protonated by acid, usually in the second step of the reaction, and that will give us a product that typically has an alcohol and a nucleophile attached to the same carbon, the carbon that used to be part of the aldehyde or the ketone. With other nucleophiles, mainly amines, the nucleophile will add, similar to the first step, leading to breaking the carbonyl, giving us a tetrahedral intermediate. But the second step of this mechanism is where the reaction differs. Instead of the tetrahedral intermediate being protonated, instead we lose a water molecule. So usually the proton transfer occurs where this oxygen is first protonated by the amine that just added in the tetrahedral intermediate, and then the lone pairs on the nitrogen will push out the water molecule to give us a double bond between carbon and the nucleophile. In most cases, this will be a nitrogen here that just added from an amine. In general, aldehydes are more reactive towards nucleophiles than ketones. One explanation for this is the fact that aldehydes are less sterically hindered. By definition, aldehydes will have a hydrogen as well as an alkyl group. So for example, here we have acetaldehyde, which has a methyl group and a hydrogen on the carbon of the carbonyl. Compare that to a typical ketone, for example, acetone, which has a couple of methyl groups. The ketone is going to be clearly more sterically hindered. Note that nucleophiles generally add at a 75-degree angle to the plane created by the carbonyl and the three groups around it. So you can see here that angle of attack comes at this 75-degree angle, and that's true for both ketones and aldehydes. An explanation for aldehydes being more reactive towards nucleophiles is the fact that there is only one alkyl group attached to the carbon. Remember, alkyl groups are electron donating. So this alkyl group would donate electron density towards this carbon and tamper down some of the reactivity of this carbon, which is electrophilic. Clearly, you can see that by the partial positive charge that it has. Compare that to a ketone, which has two alkyl groups that are electron donating, and so there will be less of a partial positive charge on this carbon of a ketone than the carbon of an aldehyde in the carbonyl. There are other factors that will alter the reactivity of certain carbonyls. For example, if we add electron withdrawing groups, generally that will make a ketone or an aldehyde more reactive than a parent aldehyde or ketone. And if we add an electron donating group, like an alkyl group, generally the carbonyl becomes less reactive. Here's an example of three different ketones. The first one has a nitro group in the benzene ring. The nitro group is an electron withdrawing group. We can clearly see that by the fact that you have a nitrogen and two oxygens, which are all electronegative atoms. And so that nitro group withdraws electron density from the carbonyl carbon of this ketone, and it makes it more electrophilic. The way you can think about it is it has more of a partial positive charge on that carbon. Compared to acetophenone, which is shown here in the middle, with no electron withdrawing group. If we add an alkyl group like a methyl group somewhere on the molecule, usually that will lead to donating electron density towards the carbonyl, and so there's less of a partial positive charge on that carbon of the carbonyl of this ketone, and so it should be less reactive than acetophenone, which is the molecule in the middle of these three examples. Generally, when we add a Bronsted or a Lewis acid to a ketone or an aldehyde, it will make that carbonyl more electrophilic than without it. We can clearly see some examples here with acetone. If we add a Bronsted acid like sulfuric acid, the oxygen of the ketone will be protonated. It puts a positive charge on the oxygen, and so that tends to act or behave like an electron withdrawing group, and so the carbon of this carbonyl becomes more electrophilic. It has more of a partial positive charge than acetone itself. The same thing happens with a Lewis acid, for example, trichloro or aluminum trichloride. When the carbonyl donates electrons to aluminum, which is a Lewis acid, it'll create an intermediate very similar to when we protonate the carbonyl. And so once again, the carbon of the carbonyl becomes more electrophilic, more reactive towards nucleophiles. Sterics around the carbonyl will also play a role in the reactivity. For example, here we have acetone and a substituted ketone with several methyl groups around the carbonyl. So we have mentioned that alkyl groups are electron donating. They generally lower the reactivity of the carbonyl. Well, when you place them near the carbonyl, it makes it even less reactive, not only because of donating electron density, but also because of sterics. So these methyl groups will hinder an incoming nucleophile that wants to react with this carbonyl carbon. Let's look at some examples of nucleophilic addition reactions. The first one we'll look at is hydration. This is where water adds as a nucleophile to a carbonyl. Generally, this reaction is slow when it's simply we simply put a carbonyl in water. We can speed up the reaction by adding an acid or a base. So we'll first look at acid catalyzed hydration of ketones and aldehydes. When an aldehyde or ketone reacts with water, we create a diol, a 1,1 diol, meaning the two alcohols will be on the same carbon. An example is shown here with acetone reacting with water, producing a hydrate or a 1,1 diol, another name for it. This reaction is reversible, meaning if we start with the hydrate, we can go back to acetone and water. The equilibrium, or where this equilibrium lies, depends on the carbonyl we're using, but in most cases, usually the carbonyl will be favored over the hydrate. One exception to that is formaldehyde. Formaldehyde, the equilibrium is favored towards the hydrate. As I mentioned previously, reaction of water with a ketone generally is slow under neutral conditions, but we can speed up the reaction if we add an acid catalyst like sulfuric acid. The equilibrium direction will not change, so acetone will still be favored over the hydrate, but we can achieve equilibrium faster by throwing in an acid catalyst. Here's a look at the mechanism for this reaction. The oxygen of the carbonyl will be protonated by sulfuric acid. Sometimes you might see this mechanism as instead of using sulfuric acid, we might see the hydronium ion here, which is the product from sulfuric acid reacting with water. This produces this protonated acetone molecule that will react then with water. Water is not the best nucleophile, and so by throwing in an acid, we can protonate this carbonyl, make it more reactive than acetone. And so this nucleophile, which is generally considered a poor nucleophile, will add to the carbonyl carbon, break the double bond to create this tetrahedral intermediate, which will then lose a proton. So we can use the conjugate basis of sulfuric acid. We could use a water molecule here to remove this hydrogen, remove the positive charge on this oxygen, and that gives us the hydrate. Ketones and aldehydes can also occur through base catalyzed reactions. For example, we can use sodium hydroxide to speed up this reaction. The base catalyzed hydration of ketones occurs this way. The hydroxide ion is a very good nucleophile, much better than water is. And so the hydroxide ion would directly attach to the carbonyl carbon and break the double bond. Compare this to the acid catalyzed hydration, where we're using water as a nucleophile. That reaction generally starts by protonating the carbonyl first, and then water can now react with a better electrophile, the protonated carbonyl. Continuing with this mechanism, once the nucleophile attacks the carbonyl, we produce this tetrahedral intermediate. The oxygen will now be protonated by water to create the hydrate. This question will take a look at the hydrate of trichloroacetoaldehyde. So take a moment to predict the product that will result from a hydration of this ketone. If water adds to trichloroacetoaldehyde, the result would be as follows. So water would add to the carbonyl, break the double bond, create this tetrahedral intermediate, which will then lead to a proton transfer. This oxygen will be protonated. This one will lose a proton to form the hydrate. And so this is the product that we get from a hydration whether it's acid catalyzed or base catalyzed of trichloroacetaldehyde. Another nucleophile we can use with aldehydes and ketones are alcohols. Addition of two equivalents of an alcohol to an aldehyde will produce an acetal. Similarly, a ketone will react with two equivalents of an alcohol to produce a ketal. Note that these two terms, acetals and ketals, are sometimes used interchangeably, and sometimes you might catch me doing the same. But technically, ketals are the products from an addition of an alcohol to a ketone, and acetals are the products that you get from an alcohol adding to an aldehyde. The reaction between alcohols and ketones and aldehydes is generally slow under neutral conditions. We can speed up that reaction by using an acid catalyst. Here's an example with cyclohexanone. If we use two equivalents of methanol and HCl as a catalyst, we can get the corresponding acetal or ketal, whichever term you want to use. Think of the product here as forming from the methoxy groups, adding to the carbonyl twice to produce this acetal. The byproduct from this reaction will be water. Now notice this reaction is reversible, and we can start with an acetal or ketal and reverse it back to the corresponding ketone by using water and an HCl catalyst or some other acid catalyst to push that reaction towards the ketone. Since this is a reversible reaction, we can take advantage of Le Chatelier's principle. So using an excess of alcohol, for example, will push the reaction towards products. Removing the water will also push the reaction towards the products. We can reverse the reaction by adding water or removing the alcohol. One simple way of doing this in a lab would be distilling the alcohol. If we were trying to get the acetal, we might distill the water or use some sort of drying agent within the reaction that will soak up the water and push the reaction towards the acetal. Look at the mechanism for an acid catalyzed alcohol addition to a ketone or aldehyde. So it starts by the ketone being protonated by the acid, in this case, hydrochloric acid. That gives you a protonated ketone. Then that allows an alcohol, which is not the best nucleophile, to add to the carbonyl carbon. This protonated ketone is now more electrophilic than the original ketone. And so upon addition of this poor nucleophile, we break the double bond of the carbonyl. We have now a tetrahedral intermediate, which loses this proton. This is the alcohol that just added. It's going to lose a proton. We could use water. We could use the chlorine from HCl that is produced from the first step. Anyways, whatever base we use is going to remove the proton and then also remove the positive charge on this oxygen. And that will lead us to this intermediate called a hemiacetal. Think of a hemiacetal as it's essentially half of an acetal. It is the halfway point between going from a ketone to an acetal. Sometimes we use the term hemiketal when we're referring to a ketone intermediate. But again, these two terms, hemiacetal and hemiketal, are used interchangeably, and I'm going to probably do that as well several times. This is the second part of the mechanism. So starting with the hemiacetal, the first step would be protonating the hemiacetal with HCl. And so the hemiacetal, you might recall, has an OH and it has an oxygen and an R group attached to that oxygen. So you can think of this as a alkoxide and an alcohol attached to the same carbon. Once you protonate the hemiacetal or hemiketal, you get this intermediate. which basically has the oxygen of the alcohol protonated. As a water molecule, it's a good leaving group, and so we can push it out by using the lone pairs on the alkoxide. Remember, the alkoxide is what we get when the alcohol adds to the carbonyl. That lone pair will push out the water molecule to give you this intermediate. So now the carbon of the what used to be the carbonyl is double bonded now to the oxygen of this ether. That makes this carbon very electrophilic. It's almost identical to a protonated carbonyl. Water, or sorry, not water, but a second molecule of an alcohol will add to this carbonyl, break the double bond, get rid of the positive charge on the oxygen. And now we have this tetrahedral intermediate. We have an OR group, and we have now a second OR group added to the same carbon. That second OR group is from this alcohol that just added, and it's still protonated because we haven't gotten rid of the hydrogen. We could do that in this step. So we could use water, we could use chlorine from HCl to pick up this proton and remove the positive charge on the oxygen, giving us the acetal or the ketal product. A little bit about the hemiacetal to ketone equilibrium. So in general, hemiacetals or hemiketals are unstable, and the equilibrium will be favored towards the carbonyl, whether it's a ketone or an aldehyde. So here's a look at what I'm referring to. If we start off with acetone and we add theoretically one equivalent of methanol, we should get a hemiketal, but that equilibrium is heavily favored towards the carbonyl. The reason for that is carbonyls, the double bond here is a strong bond, and so it favors the equilibrium backwards. Now, the exception to that rule is cyclic hemiacetals or cyclic ketals. So in other words, if we can obtain a fairly stable cyclic hemiacetal or hemiketal, generally that would be the favorite product or the favorite molecule. So here's a look at an example. If we have an aldehyde and an alcohol that are attached to each other, if we add, or actually if we just let them be, the alcohol will add to this carbon, and the double bond here will be turned into an OH when this oxygen is protonated. So we'll pick up a proton from this alcohol. You'll end up with a cyclic hemiacetal. In this example, the product, the cyclic hemiacetal, is favored over the original aldehyde. One of the best known examples of cyclic hemiacetals is glucose, but this is also true for many simple sugars that can form stable 5 and 6 member rings. So using glucose as an example, we can draw glucose in an open form or in a cyclic form. So this is one way to draw it. This is a straight chain glucose. Glucose has an aldehyde. It has several alcohols. Pretty much every carbon in the six carbon chain has an alcohol. And the one on carbon 5 likes to attack the aldehyde. So here is how that would happen. So here is carbon 5 with this alcohol. That oxygen will attack this carbonyl and form a cyclic hemiacetal. Now, because this is going to lead to a 6-member ring, there's 2 possible conformations that we can draw. We can have this OH that is a result of the carbonyl becoming protonated after attack of the oxygen on carbon 5. This OH can be equatorial, as shown here, or it could be axial, as shown here. As we know from Organic Chemistry 1, equatorial is usually favored, and so it's no surprise that At equilibrium, 69% of all molecules will be found, 63% of all molecules will be found in this form, this conformation, where the OH is equatorial. Only 37% will exist with the OH being axial, and then less than 1% will exist in this open form. Glucose forms two well-known polymers called cellulose and starch. Starch is a polymer that forms by glucose molecules making this sugar bond. So on the sugar on the left, we see an axial bond, and that's attached to an axial position of the next sugar unit. And this repeats multiple times to make the polymer, which we call starch. Polymers in general, if you're unfamiliar with that term, just means a very large molecule that has multiple repeating units of the same monomer. In this case, for starch, it would be glucose. Second polymer that glucose makes is cellulose. It is formed by taking multiple sugar units and making a sugar bond that is equatorial on both sugar units that are connected. Note that humans are not able to metabolize cellulose since they don't have an enzyme that can digest or break down this bond here, which is equatorial. We do, however, have an enzyme that is able to digest the axial bond of starch. One last point that I want to make here is that notice the connection between the two sugar units next to each other is essentially an acetal bond. So if we focus in on this carbon here, we have an oxygen and an alkyl group. And then on the other end, we have an oxygen and an alkyl group. So there are two alkoxide groups going to the same carbon. That is what an acetal is. The same thing occurs with cellulose. So this carbon here will have two alkoxide groups attached to it. So that is also an acetal. Acetals can be used as a protecting group for ketones and aldehydes. Acetals essentially behave like an ether, and so they're very stable. They're stable to bases, nucleophiles, reducing agents, oxidizing agents. The only thing that they're really susceptible to is acidic aqueous conditions, as we'll see in a moment. Now, for protecting aldehydes and ketones, we generally will use a diol, although we don't have to. Diols make it easier to form a cyclic acetal or ketal. That usually is easier to do than just making an acetal out of two equivalents of an alcohol. Here's an example using this ester that also contains a ketone. If we add a diol and an acid catalyst, we can make an acetal from the ketone. Notice that we don't do anything to the ester in this reaction. Now, in predicting the product, we want to look at the diol we're using. This one has two carbons. So the acetal will also have two carbons, and they're attached to each other, making a 5-member ring to the carbonyl carbon that used to be there. A byproduct of this reaction will be water. And so this reaction, just like any acetal formation, is reversible. If we wanted to remove the acetal protecting group, we can do it with the aqueous acid. Now in this example, I want to illustrate the power of acetals as a protecting group. For example, if we wanted to do a reduction on the ester, that ketone would get in the way because ketones are more reactive towards nucleophiles like hydrides than esters are. So we have to protect the ketone first, and then we could do the hydride reduction of the ester to get a primary alcohol. And then once we're done with that reaction, we could remove this protecting group by using aqueous acid essentially reversing the formation of the acetal. That would lead us to the ketone plus the diol byproduct. In this question, we're going to try to predict the ketal that is formed from an acid-catalyzed reaction on 2-pentanone with a diol called 1,3-propane diol. So try to do this first before looking at the next slide. 2-pentanone will react with 1,3-propane diol in an acid catalyst to make the corresponding acetal. So the way we want to predict the product is if we take this oxygen and bind it to this carbon, and then we have 1, 2, 3 carbons. So in the product, we'll have 1, 2, 3 carbons, and then the next oxygen will be attached to that carbon and also attached to the carbonyl carbon. And so the result is a 6-member ring involving 2 oxygens attached to the same carbon. The byproduct will be water. When it comes to amines generally will produce 2 potential products from a ketone or an aldehyde, either an imine or an enamine. The product will depend on what type of amine we use. If we use a primary amine or ammonia, typically we end up with an imine, which you can recognize as having a carbon to nitrogen double bond. Sometimes these imines are called Schiff bases. Another possibility is if we use a secondary amine. Secondary amines will produce instead an enamine. An enamine will have a carbon to carbon double bond and a nitrogen to carbon single bond on the same carbon. If you look closely, enamines are very similar to enols. Let's take a closer look at the reaction between ammonia or primary amines with ketones and aldehydes to produce imines. Here's an example with an aldehyde. If we use a primary amine, you can recognize primary amines by the fact that they have 2 hydrogens in 1 alkyl group. Use a catalytic amount of acid like HCl will produce an imine. So in order to draw the product, you want to take the nitrogen from the amine, place it where the oxygen of the carbonyl used to be, put a double bond there, and whatever alkyl group is on the nitrogen to begin with will also be in the product. The byproduct of this reaction will always be water. This reaction is reversible, so as you'll see in a moment, we can go back from or go from an imine back to the aldehyde by adding water and an acid. Here's another example with a ketone, catalytic amount of HCl, and if we use ammonia, we will get an imine. So notice again, there's a nitrogen to carbon double bond where the carbonyl used to be. In the case of ammonia, instead of having an alkyl group, we have a hydrogen, so you'll have a hydrogen there. We could also use a primary amine here. The result of that would be similar, a similar function group, except there will be an R group where the hydrogen is. This reaction will also produce water, and it is reversible. The reaction works best around a pH of roughly 5, so slightly acidic conditions. Here's the mechanism for the addition of a primary amine or ammonia to a ketone or aldehyde. If we have a primary amine, it will add to the carbon of the carbonyl. So amines are better nucleophiles than water and alcohols, so they can add directly to the carbonyl carbon without the need of an acid first. That gives us an intermediate, a tetrahedral intermediate. And so the next step will be a proton transfer. This oxygen has a negative charge, so it wants a proton. And this nitrogen has a positive charge, so it wants to lose a proton. So this proton from the nitrogen will be transferred over to this oxygen. And usually this is shown in two steps, where a base removes the hydrogen and then it will give it to this oxygen. In the next step, which is starts off with a carbonyl amine, the oxygen will be protonated by acid to give us a water molecule. And then this nitrogen can push it out through the lone pairs. And so in the next step, you'll see that there will be a double bond here between carbon and the nitrogen. Continues with an iminium ion being formed. So after the nitrogen has pushed out the water molecule, we'll have a double bond here between nitrogen and carbon. We'll also have a proton on this nitrogen that we're going to remove by using water or some other base in the reaction. And then that would also get rid of the positive charge on the nitrogen. That gives us the final product, which is an imine. As I mentioned previously, the formation of an imine is a reversible reaction. So if we add water, which is the byproduct of imine formation, and we also add HCl, we can reverse that reaction. So here's an example with an imine. If we add catalytic amount of HCl and water, we can turn that imine into a ketone, and you can tell it's going to be a ketone by the fact that this imine is at a carbon that has two alkyl groups. So that same carbon will now turn into a carbonyl. The byproduct would be an amine. The amine, you can tell which one is going to be by the fact that we have a nitrogen, a hydrogen, and a methyl group attached to that nitrogen. So adding an extra hydrogen will give us the byproduct from this reaction. Unlike primary amines, which typically give you imines as products, secondary amines will give you an enamine. As you'll see in a moment, the mechanism will explain why that is. Here we have a ketone, an unsymmetrical ketone. If we add a catalytic amount of HCl and a secondary amine, we'll form the corresponding enamine. Notice that in the reaction of an unsymmetrical ketone, the enamine will always form towards the more substituted side. So you can see that the double bond is towards this methyl group as opposed to the right side of this cyclohexane. On the same carbon of the double bond, we'll have a bond to a nitrogen, which will have two methyl groups, since that is related to this secondary amine that we use here, which has also two methyl groups. The byproduct of this reaction will be water, and this reaction is also reversible, although it's not shown here. This reaction, if we add water and HCl to an enamine, we can make it go back towards the ketone. Here's an example with an aldehyde. If we use HCl and a secondary amine, we can get the corresponding enamines. Aldehydes only have one alkyl group, so there's only one possible place where we can put the double bond. So the double bond will be here, where to attach between two carbons. It is starting where the carbonyl used to be. On this carbon, we'll also have a nitrogen and two alkyl groups. If the secondary amine has two ethyl groups, we'll have two ethyl groups on the nitrogen of the enamine. Byproduct will be water. This reaction, again, is reversible. We can make it go back to the aldehyde by adding water to the reaction. The mechanism for the formation of an enamine, for the first half of the mechanism, it will be identical to the mechanism as forming or when forming an imine. Let's take a look at how this happens. Starting with an aldehyde or ketone, if we add a secondary amine, the secondary amine will add to the carbonyl carbon. Eventually, after a proton transfer, we'll have this carbonyl amine intermediate. So you'll have an alcohol and an amine on the same carbon, making it a carbonyl amine intermediate. In the next step, the oxygen will be protonated, forming water, and in the next step after that, the nitrogen will push out that water to give us an iminium ion, which you'll see on the next slide. Once we get to the iminium ion, this is where things differ between using a secondary amine and a primary amine. In the case of a primary amine, when we get to this iminium ion, we have a hydrogen where this R group is. So the next step was always to remove that hydrogen and basically get rid of the positive charge on the nitrogen. And that led to an imine being formed when we use a primary amine. In the case shown here, we're dealing with a secondary amine that added, forming this iminium ion. And secondary amines by nature have two alkyl groups, as shown here. So when we add base to this step of the mechanism, we cannot remove a hydrogen. And so the only thing that we can do to get rid of this positive charge is remove a hydrogen from an alpha carbon. In other words, a carbon adjacent to the iminium ion double bond. So a base, such as water, will remove this hydrogen, form a double bond there, get rid of this double bond, and put those electrons on the nitrogen to get rid of the positive charge. So that leads us to the final product, an enamine. Similar to imine formation, in the cases of enamines, we can reverse the reaction by adding water and HCl. So as shown here with this example, this enamine will be turned to the corresponding carbonyl and a secondary amine. You can predict the products based on what we're seeing here. So we have a carbon to nitrogen single bond that will turn into a carbonyl, and the amine that is shown here in the enamine will then be expelled. So the nitrogen has to pick up a proton and will become a secondary amine. Amines come in other variations besides your typical primary or secondary amines. So there are certain amine-like molecules like hydrazine, which contain an NH2 bonded to another NH2. And these types of molecules will form what we refer to as imine derivatives when they're mixed with a ketone or an aldehyde. So for example, hydrazine, when mixed with this ketone and HCl, will form a imine derivative called a hydrazone. So hydrozones are imines of hydrazine. And you can see in the product, we basically have an imine bond between a carbon that used to be part of the carbonyl and the nitrogen of hydrazine. Hydrazine has another NH2 attached to that nitrogen, so that's what you see here in the product. We have water as a byproduct, and also this reaction is reversible, so as you'll see in a moment, we can turn a hydrazone into a ketone in hydrazine by adding acid and water. Another example of an imine derivatives or imine derivative is a hydrazone that has a couple of nitro groups on a benzene ring. So this is referred to as a 2,4-dinitrophenylhydrazine or hydrazone once it becomes the product. So here's an example with acetone mixing with this 2,4-dinitrophenylhydrazine to form an imine derivative, which is a hydrazone. A byproduct of this reaction will be water, and again, this reaction can be reversed by adding water and HCl. A couple of more examples of imine derivatives. So cyclohexanone, when mixed with hydroxylamine, which is NH2 bonded to an OH, will form an oxime. An oxime is another example of a imine derivative. So in the case of hydroxylamine, note that the nitrogen is more nucleophilic than the oxygen. So the nitrogen will attack the carbonyl carbon and form eventually a double bond there. And the OH essentially acts as a substituent that rides along for the reaction and is found in the product. This oxygen from the carbonyl will eventually become a water molecule and it will be a byproduct of the reaction. The reaction again is reversible by adding water and HCl. Here's another example with hydroxylamine again and a different ketone. If we add HCl, we can form the corresponding oxime and water as a product. Note that many imine derivatives are highly crystalline, and so sometimes, especially if you don't own an NMR, which is a pretty expensive instrument, certain labs will turn ketones and aldehydes into imine derivatives, and they'll take the melting points and figure out the other physical properties and use those to determine or confirm the structure of an unknown. Aldehydes or ketones can be determined or confirmed, their structures confirmed by turning them into a 2,4-dinitro-hydrazone, as shown here in this reaction. This product is highly crystalline. It also forms a very red color. Those characteristics plus the melting point will allow a particular ketone to be compared with a set of standards, and you can use that to determine or confirm the structure of a particular unknown aldehyde or ketone. Of course, if you have NMR and IR and mass spec available, those methods would be would make it a lot easier to identify the unknown. But in certain labs, those are not available due to cost, and so this is a simple method to determine or confirm the structure of an unknown aldehyde or ketone. Or oximes and hydrozones and other imine derivatives can be hydrolyzed and converted into the corresponding aldehyde or ketone. Here's a couple examples, starting with an oxide. If we add water and HCl, we can convert it to the corresponding ketone plus hydroxylamine. You can tell you're going to get hydroxylamine by the fact that the nitrogen has an OH in the imine derivative. And then the ketone will simply come from the converting this imine bond to a carbonyl, which you see here in the product. With the next example, we start off with a hydrazone. And so this hydrazone will be converted into a carbonyl and we'll get a hydrazine byproduct. Beta-carotene is a natural compound that has multiple double bonds that are conjugated to each other. This conjugation gives beta-carotene an orange color, and many fruits and vegetables like carrots and mangoes and cantaloupes have this orange color due to beta-carotene. Beta-carotene is a compound that is converted in our bodies into cis-retinal by an oxidation reaction that turns or gives the product an aldehyde. This aldehyde will react with the amino group of a protein called opsin to form an imine bond, similar to the reactions we learned in this chapter. And rhodopsin, which is the product from this reaction, is a light-sensitive protein found in the retina of our eyes, and is essential for low-light vision. Nucleic acid bases cytosine and uracil can be interconverted through a tautomerization followed by a deamination reaction. Starting with cytosine, we can convert this amino group into an imine through a tautomerization reaction. Notice the double bond shifts from being in between this carbon and nitrogen to being in the other carbon and nitrogen in the amino tautomer. Hydrolysis of this imine by adding water will lead to a carbonyl being formed, which is the structure of uracil. Cytosine is found both in DNA and RNA, while uracil is found in only RNA. In this question, we'll practice the acid-catalyzed addition of amines to cyclohexanone. In the first question, we're using a primary amine. In the second question, we'll use a secondary amine. Ketones and aldehydes can be reduced completely and turned into an alkane by a reaction called the Wolff-Kishner reaction. As an example, starting with a ketone, if we add hydrazine, we'll initially get a imine derivative, a hydrazone, which will then react with base while heating to be eliminated into an alkane. The reaction produces N2 gas and water as a byproduct. Note that evaporation of this nitrogen gas essentially turns the reaction into an irreversible reaction since it will be difficult to capture the nitrogen gas after it has evaporated. In the second example, we're using acetophenone reacting with hydrazine. Again, under basic conditions while heating, will remove completely the carbonyl and produce nitrogen gas and water as byproducts. Let's take a look now at the mechanism for the Wolff-Kishner reaction. The reaction starts by hydrazine attacking the carbonyl of the ketone or aldehyde, and then through a series of steps, we will eventually produce the imine derivative, which we see here. Note that this is the same mechanism we saw in the last section. Addition of base to the imine derivative will result in removing this hydrogen, putting a negative charge on the nitrogen, as shown here. And then that nitrogen will push electron towards the carbon to put a negative charge on the carbon. Note that these are resonant structures of each other. Water will then protonate that carbon to produce the intermediate that we see here. If we repeat the same two steps again by adding base, removing this hydrogen, and eventually putting a negative charge on this carbon, we can continue the reaction. In the last couple of steps of the mechanism, the nitrogen will be removed as N2 gas, and it results in a negative charge on the carbon. Addition of water will protonate the negative charge on the carbon, as shown here. So this carbon will pick up a proton from the water to add an extra hydrogen there, and overall we have turned the ketone into. Here's another example of a ketone being reduced with hydrazine and under basic conditions. So this ketone is completely removed into the corresponding alkane. Note that we have the same number of carbons, so there are 3 attached to the ring. We'll have 3 in the product as well. We can do the same reaction with aldehydes, so this aldehyde will be reduced under the Wolff-Kishner reaction into the corresponding alkane. Let's now practice some examples of the Wolff-Kishner reaction. So the question here asks us to show how you would prepare the following compound, which is shown here, from the following ketone, which is 4-methylpent-3-ene 2-one. And in the next reaction, we're going to take 4-methylpentane 2-one and attempt to convert it into this alkane. So the reaction is essentially asking us to give the reagents for the reaction. In order to turn this ketone here into the corresponding alkane, we will use the Wolff-Kishner reaction. So that involves hydrazine, potassium hydroxide, and although it's not shown here, we generally will heat this reaction well over 100 degrees. We can do the same reaction with the ketone on the bottom under the same reaction conditions. A complementary reaction to the Wolff-Kishner reaction is the Clemmensen reduction. So this reaction does the same thing as the Wolff-Kishner. It turns ketones and aldehydes into alkanes. However, it does it under acidic conditions. So here's an example of the Clemmensen reduction. Starting with a ketone, if we add HCl, zinc, and mercury, we can convert it into an alkane. We can remove an aldehyde carbonyl in a similar fashion under HCl, zinc, and mercury. Notice that we retain the same number of carbons in the product. Reaction in organic chemistry is called the Wittig reaction. This reaction starts off with triphenylphosphine. We add that to an alkylating agent such as methyl bromide. Through an SN2 reaction, this phosphorus will attack the carbon, eliminate the leaving group, and form a phosphonium salt. Phosphonium salts will have a positive charge on the phosphorus, which makes the hydrogens on this carbon fairly acidic. We can add a strong base like butyllithium to remove one of these hydrogens and therefore produce what we call a Wittig reagent or a phosphonium illet. The phosphonium illet will have a negative charge on the carbon, which makes that carbon very nucleophilic, and it also will have a positive charge on this phosphorus. Illets are compounds that contain both a positive and a negative charge on adjacent atoms. So a good example of that is a phosphonium illet. Phosphonium means there's a positive charge on phosphorus, and illet means there is an adjacent negative charge, in this case on a CH2 group. Phosphonium illets contain two resonance forms, so sometimes they're drawn like this with a positive and a negative charge, or we could use the lone pair from the carbon to form a double bond between the carbon and phosphorus, and you could have a resonance structure as shown on the right here. Either way, we have a nucleophilic carbon next to the phosphorus, which allows the Wittig reaction to occur. The Wittig reaction is used to convert a carbonyl, like a ketone or aldehyde, into an alkene. Here's an example with cyclopentanone. Using this Wittig reagent, we transfer the CH2 and the double bond into the product. So as you can see, this carbon that is part of the double bond on the end, it has two hydrogens, just like the Wittig reagent. So you can essentially visualize this reaction as swapping an oxygen for a CH2 group. Some Wittig reagents, as you'll see in a moment, will contain alkyl groups rather than hydrogens, and those will be transferred as well. The byproduct of the Wittig reaction is always triphenylphosphine oxide, which is a sometimes difficult to remove byproduct. Sometimes when we do chromatography to purify our desired product, sometimes it is very difficult to remove this compound. The mechanism for the Wittig reaction occurs as follows. So the Wittig reagent involves a carbon that is nucleophilic. That carbon will attack the carbon of the carbonyl. It will produce this intermediate, which will lead to the oxygen and its negative charge attacking the phosphorus with its positive charge, forming this four-member ring. That four-member ring is very strained and it will decompose to either go back to the original ketone or illet or go forward into producing this alkene and triphenylphosphine oxide. Note that the phosphorus to oxygen double bond is a very strong bond, and so there is a driving force to produce these two products that you see here at the end. If we use an unsymmetrical Vidic reagent and an unsymmetrical aldehyde or ketone, we can produce a product that has a mixture of E and Z isomers. In general, alkyl ylids, so as shown here, typically will give the Z isomer. However, there are conditions we can use to produce the E isomer. We won't go into those details. For our course, just assume that you can get whichever isomer you need. Note that esters and amides don't really react with Vidic reagents, so we can do a Vidic reaction with an aldehyde or ketone in the presence of one of these functional groups. Also, a hydrogenation reaction of the alkene product will allow you to overall convert a carbonyl into an alkyl substituent. Here's an example to illustrate those 2 points. This compound has a ketone on the left and an amide on the right. If we do a Vidic reaction with this Vidic reagent, we will add the Vidic reagent, or at least the alkyl group on it, to where the carbonyl of the ketone was. Notice there are 1, 2, and 3 carbons. So 1, 2, and 3 carbons will be added where the carbonyl, the ketone was. Nothing happens to the amide. Now notice in this product, there is no double bond. That is because we're doing a hydrogenation reaction following the Vidic reaction. Normally, we would obtain a double bond here where the carbonyl used to be, but if we do a hydrogenation, we'll get an alkane there instead. The Vidic reaction is a reaction that has been used for a number of syntheses of important biological molecules. For example, it has been used to synthesize vitamin A. In this synthesis, an aldehyde, as shown on the right, was used. Notice it had also an ester in the molecule. And mixing that with a phosphonium salt will lead to producing a Vidic reagent by addition of base. So sodium methoxide will deprotonate one of the hydrogens on the CH2 group, turning that into a Vidic reagent. Under reversible conditions, meaning under or with a protic solvent, we can allow the E isomer to be favored. This Vidic reagent will react with the aldehyde to produce the double bond highlighted here in color. Again, because of the reversible conditions, we obtain the E isomer. If we didn't have these reversible conditions, we would obtain the E isomer instead. This question, we will use the Vidic reaction to produce the following 2 alkenes. So the question asks what carbonyl compound and what phosphorus illet would be used to prepare the following compounds. In order to think about the Vidic reaction backwards, we want to think about splitting the double bond of the product, the alkene, into 2 parts, turning one side into a ketone and the other side into an illet. So as you can see here, we obtain, or we would do this reaction from cyclohexanone and the following illet. So the illet always has triphenylphosphine attached to the alkyl group that we're going to add to the carbonyl. Now, you might recall that Vidic reagents are typically made from an SN2 reaction. Typically, it involves triphenylphosphine adding, so that would be the following compound, triphenyl, so 3 phenyl groups attached to a phosphorus, and that typically reacts with an alkyl halide through an SN2 reaction. For that reason, we want to make sure that the alkyl halide does not have a lot of sterics. So if we wanted to make the following Wittig reagent, we would use perhaps ethyl bromide as shown here, and that should lead to the following Wittig reagent after we use base. So initially you'll produce a phosphonium salt, and then base will remove the acidic hydrogen. So imagine this having a CH2 group. A base like butyllithium will remove a hydrogen from there to produce this Wittig reagent. We can draw the Wittig reagent as shown here, or we could get rid of those charges and instead add a double bond here. Either way is fine. Now, my main point that I wanted to make here is that because this Wittig reagent is made from an SN2 reaction, we want to make sure that there isn't a lot of sterics around the alkyl halide in order to produce it. So ideally, a primary alkyl halide would work best. So for that reason, in order to make this ketone, we would want to use this particular Wittig reagent and this particular ketone as opposed to breaking the double bond the other way, where this becomes the ketone and this becomes the alkyl halide. That would make the alkyl halide a secondary alkyl halide plus it is part of a cyclohexane ring, which are not helpful for the SN2 reaction. In the next example, again, if we split the double bond, we can make one side a ketone, the other side a alkyl halide. So given that this carbon has two alkyl groups, we want to turn that into a ketone, which would be acetone. And then on the left side, the carbon has a hydrogen and a phenyl ring, so that would be a primary alkyl halide we can use to make the following Wittig reagents. Let's now review a reaction that we've seen previously in the chapter with alcohols. So you might recall that ketones and aldehydes will react with Grignards and organolithiums in order to produce an alcohol. So if we start off with a ketone and we add a phenyl Grignard or phenyl lithium reagent, we would transfer a phenyl group to the carbon of the carbonyl and turn the ketone into a tertiary alcohol. With aldehydes, when we react with Grignards and organolithiums, we'll transfer the alkyl group to the aldehyde carbon. So in this example, the CH3 group shown here will add to this carbon and turn that carbon into a secondary carbon now, and the product will be turned into an alcohol, a secondary alcohol. We can add a cyanide nucleophile to aldehydes and ketones as shown in this reaction. So typically the reaction will involve catalytic amount of potassium cyanide and a large amount of cyanide gas. So this is a pretty dangerous reaction, but it allows us to turn an aldehyde into a cyanohydrin, which is a functional group involving a carbon that has both a cyano group and a hydroxyl group. Here's the mechanism of the reaction. The cyanide ion will add to the carbonyl carbon, break the double bond to give us this tetrahedral intermediate. The oxygen will then be protonated by cyanide gas to produce the cyanohydrin and the cyanide ion, which will continue the reaction. So for that reason, we only need a catalytic amount of potassium cyanide. Note that cyanide ion is not a strong enough nucleophile to react with esters and amides, so it generally reacts only with aldehydes and ketones. Certain species of millipedes as well as plants release hydrogen cyanide as a deterrent for animals that threaten them. For example, millipedes will use this sugar compound that they obtain from their diet of fruits, for example, from apricots or wild cherries or peaches, and they will, when threatened, convert it into mandelonitrile, which is a compound that is a cyanohydrin. This cyanohydrin can expel hydrogen cyanide, and therefore it can be used to deter animals from eating or bothering the millipedes. The reactions we just covered, we want to attack this question, which will ask us to show the structure of the cyanohydrin obtained from cyclohexanone. If we use cyclohexanone to make a cyanohydrin, the reaction will occur as follows. So the carbonyl carbon will be attacked by cyanide to produce this tetrahedral intermediate, which will then be protonated to produce the following cyanohydrin. Beta unsaturated carbonyls are an important reactant in many reactions. These are interesting compounds since they can undergo two types of additions with nucleophiles. For example, nucleophiles can add to alpha-beta unsaturated carbonyls by attacking the carbon of the carbonyl, producing this tetrahedral intermediate, which are then protonated to become a product that you see here. This is what we refer to as a direct or a 1,2 addition. This reaction is actually what we saw in the last few sections with nucleophiles adding to carbonyls of aldehydes and ketones. Now, if you have an alpha-beta unsaturated carbonyl, an additional reaction besides direct addition to the carbonyl is addition to the beta carbon of the alpha-beta unsaturated carbonyl. In case you're unfamiliar with the terminology, alpha-beta unsaturated carbonyls are compounds like these that contain a site of unsaturation between the alpha carbon, which is the carbon next to the carbonyl, and the beta carbon, which is the next carbon over. This double bond here, as well as the carbonyl, have two sites that are electrophilic, in other words, two sites where a nucleophile can add. The nucleophile can add to the beta carbon, or it can add directly to the carbonyl carbon. Adding directly to the carbonyl carbon, again, is called direct or 1,2 addition. Adding to the beta carbon is called conjugate or 1,4 addition. When a nucleophile attacks the beta carbon, the product that we obtain will look like this initially. So there will be a negative charge on the oxygen, which can be protonated to produce essentially, or at the end, this saturated aldehyde or ketone. Perhaps an easier way to visualize this is using this other resonance form, which is an enolate. We'll talk about those later. Enolates will be protonated and produce the saturated aldehyde or ketone. Going back to this intermediate, the way you can think about this reaction is we have here an enolate, a resonance form of the enolate. If that gets protonated, the result, if you imagine adding a hydrogen here, would be an enol. And as we learn, enols are easily converted through tautomerization into carbonyls. Strong nucleophiles like Grignards and organolithiums will add irreversibly to the carbonyl of an alpha-beta unsaturated carbonyl, such as the one shown here. In this example, the ethyl group will be transferred to the carbonyl carbon and give you a tertiary alcohol with an extra ethyl group. Now, this addition is considered a direct or a 1,2 addition, and it typically gives you the fastest forming product. So in other words, adding this ethyl group to the carbonyl is faster than adding it to the beta carbon. And so as a result, we get what we call the kinetic product. In other words, the product that forms the fastest. And another example of a very strong nucleophile that would add irreversibly and will add to the carbonyl carbon of an alpha beta unsaturated carbonyl would be lithium aluminum hydride. So this is a reagent that produces hydrides, and that hydrogen will add to this carbon, turning the ketone into an alcohol. Moderate nucleophiles generally will do a reversible addition to both the carbonyl carbon as well as the beta carbon. And at the end of the reaction, the product that we typically obtain is the one that results from 1,4 addition. In other words, adding to the beta carbon. So in this example, using a thiol, which would be considered a moderate nucleophile, at least in relationship to Grignards and hydrides, the sulfur will add to both the carbonyl carbon and to the beta carbon. And at the end of the reaction, the most stable product, what we call the thermodynamic product, will be the product that we get from the reaction. So that is true for any reversible reaction. So in this example, the sulfur, the thiol, will add to the beta carbon, eventually getting rid of this double bond after the addition of a hydrogen to the alpha carbon. And so in the product, we will have a sulfide substituent added to the beta carbon. The double bond will be gone and the carbonyl still intact. Another moderate nucleophile is the cyanide ion that generally adds to the beta carbon, and cuprates or Gilman reagents will also add an alkyl group to the beta carbon. So these are the cuprates, that is, are examples of carbanions, but unlike Grignards and organolithiums, they're considered more moderate nucleophiles, and so they generally add to the beta carbon. Note that although I'm showing examples here with ketones, alpha beta unsaturated ketones, the reaction works the same whether we use an alpha beta unsaturated ketone or an aldehyde or ester or amide or other similar carbonyl compounds. One last point here, the reason why the addition occurs at the beta carbon due to this reversible reaction is because a carbon-carbon bond is a weaker bond than a carbon-oxygen double bond. And so when we have reversible conditions, getting rid of the double bond is favorable due to the fact that we're getting rid of a weaker bond compared to a stronger bond. Under kinetic conditions, which is what we saw in the previous slide with strong nucleophiles, the addition just happens through a mechanism that is the fastest mechanism, which is the addition of the carbonyl carbon. So in that case, the reaction wasn't reversible, so we only get the addition that occurs the fastest, which is the addition of a nucleophile, strong nucleophile, to the carbonyl carbon. Mentioned before, Grignards and organolithiums are much stronger nucleophiles than the milder cuprates. So cuprates generally will do an addition that is reversible to the beta carbon. So it will result in this product. And Grignards and organolithiums will add irreversibly to the carbonyl carbon and produce the kinetic product. So it is the one shown here. Notice the double bond is intact in the direct addition, while in the conjugate addition, which is what we get with cuprates, we get an addition to the beta carbon, and the carbonyl is the one that is intact. Isocitrate is a molecule that is biosynthesized through a conjugate addition of water. So it starts off with this alpha beta unsaturated carboxylate. So here we have the conjugate base of a carboxylic acid, which we call a carboxylate. And there's an alpha beta double bond here. Through this enzyme shown here, water will be added to the beta carbon and result in isocitrate, which has an alcohol. There are several anti-cancer drugs that contain an alpha-beta unsaturated carbonyl of some sort. For example, this anti-cancer drug shown here, vernolopin, has an alpha-beta unsaturated double bond that is next to this lactone or cyclic ester. These compounds are able to stop cancer by the fact that DNA polymerase contains a thiol group, which is a key nucleophile or a key enzyme in the polymerization of DNA, and therefore is very important in the spread of cancer or the replication of cancer cells. However, if we throw in an anti-cancer drug such as this one here, that thiol group will add to the beta carbon of this alpha beta unsaturated carbonyl and be linked to it and therefore be inactive. So DNA polymerase will no longer be able to help cancer cells replicate. There are a few more examples shown here of other alpha-beta unsaturated carbonyl drugs that are anti-cancerous for the same or through the same mechanism. So we can see here an alpha-beta unsaturated carbonyl highlighted also here in blue. And then here we have a highlighted alpha-beta unsaturated ketone. In this question, we want to predict which lithium diorganocopper reagent or which Gilman reagent we want to use, as well as which alpha beta unsaturated carbonyl we want to use in order to synthesize these two compounds that you see here. As a reminder, lithium diorganocuprates or copper reagents are compounds that add reversibly to the beta carbon. And so when looking at the two products that we have in this question, so here is the first one. We have a ketone, and at the beta carbon, so if you count, this is carbon 1, this is carbon 2, this is the beta carbon. We're adding, or it looks like we're adding this substituent here. So if you imagine putting together a lithium copper reagent that has the same alkyl group twice, so a CH2 bonded to a CH2 as shown here. We have now the copper reagent, or the Gilman reagent we need to do this reaction. And then we need to turn the ketone in the product into a double bond between the alpha and beta carbon. So using this ketone, this alpha beta unsaturated ketone, and this cuprate, we can make the product that is part of the question. In the other example, we started with this compound and using a Gilman reagent, again, we will be doing an addition to the beta carbon of the ketone. So if this is the ketone, this is the alpha position, this is the beta position, we want to add this propyl group. So our Gilman reagent will have lithium with two ethyl groups attached to copper. And then we would be adding that to an alpha beta unsaturated carbonyl. So alpha beta position has a double bond, and that is next to this ketone. Summarize this chapter by looking at or looking through some of the reactions we learned about. So in this first reaction, we have an acid chloride, and we're adding a Gilman reagent. In the second example, we're starting with an ester. We're adding diol at negative 78 degrees and following that up with aqueous acid. In this third reaction, we start with a terminal alkyne, and we're going to add mercury sulfate, sulfuric acid, and water. In the next reaction, we use a terminal alkyne, and we do a hydroboration reaction. And then lastly, starting with an alcohol, we add chromic acid in this reaction. If we add a Gilman reagent to an acid chloride, one of these two methyl groups will be replacing the chlorine to give us a ketone that has a methyl group. Diol is typically used to convert an ester into an aldehyde under these conditions. Mercury sulfate, sulfuric acid, and water will lead to an oxymercuration of this alkyne. So initially, you'll get the more substituted carbonyl, which would be a carbonyl on this carbon, the internal carbon. And so you'll end up with a ketone that has a methyl group, which is this carbon at the end, plus 1, 2, 3 more carbons. So that would be 1, 2, 3 carbons. Hydroboration of the same terminal alkyne will lead to an addition of a carbonyl at the least substituted carbon. And so you'll end up with an aldehyde that has 1, 2, 3, and 4 carbons, which are shown here, 1, 2, 3, and 4. Chromic acid will oxidize secondary alcohols into a ketone. First reaction here, we're going to start with a ketone and add HCl in an excess of alcohol. In the next reaction, we're going to use an acetal or ketal and add a catalytic amount of HCl plus water. In the next reaction, a ketone, HCl, and a secondary amine. In the fourth reaction, we're using a ketone, catalytic amount of HCl, and a primary amine. And then lastly, we're going to use a ketone, catalytic amount HCl, and hydrazine. Start with a ketone and add HCl and an excess of ethanol. We'll make an acetal or a ketal from that reaction. So the way to predict this is you take the ethanol, you're going to add that twice to this carbon, and so you'll have two ethoxy groups in the product. This oxygen from the ketone will be converted into a water molecule. We can reverse this reaction as shown on the next example by adding HCl and water to a ketal or an acetal. So in order to produce the product, you want to look at this ketal and then put a carbonyl where this acetal is. And if you look at the acetal, it has two methoxy groups, so the byproduct would be 2 molecules of methanol. In the next example, we're starting with a ketone and we're adding HCl in a secondary amine. So the product would be an enamine. So the nitrogen will add where the carbonyl is as a single bond, and then you'll have a double bond towards the more substituted side. So enamines, very similar to alkenes, will be more stable when they're more substituted. So rather than go to the CH3, the double bond will be facing in this direction towards the cyclohexane ring. The nitrogen has a couple of ethyl groups, so you're going to see that in the product as shown here. And then the oxygen of the carbonyl becomes a water molecule. If we add a primary amine instead, we won't get an enamine, but we'll get an imine, which is a nitrogen to carbon double bond. The nitrogen of the amine, which is a primary amine, has a methyl group, and so we see that methyl group being transferred to the product. The oxygen, again, will be converted into a water molecule. If we use a carbonyl and add hydrazine, we'll instead get an imine derivative. So very similar to an imine. In this case, an NH2 group is attached to the hydrazine, so that will also be attached in the product. In the first reaction here, we're starting with an oxime, which is a product of an addition of hydroxylamine to ketone. Here we're looking at the reversal of that reaction. So this oxime, we're going to add HCl and water. In the next reaction, we have a ketone and we're going to add hydrazine. But this time we're going to do it under basic conditions and we're going to heat it up. So this is an example of the Wolff kitchen. We could do a similar reaction with HCl, zinc, and mercury, which is the Clemmensen reduction. In the next reaction, we're starting with a ketone and we're going to add a Wittig reagent through the Wittig reaction. In the next example, we're using a ketone and we're going to add Grignard or organolithium. And then lastly, we're going to take an aldehyde and add chromic acid to it. If we start off with an oxime and we add HCl and water, we're going to reverse a reaction that led us to this oxime. So in this example, water would replace this imine derivative into a carbonyl, and we'll have hydroxylamine as a byproduct. In the next reaction, we're going to do either a Wolff-Kishner or a Clemmensen reduction to completely remove this carbonyl and obtain an alkane. The Wittig reaction will convert a ketone into an alkene. Notice we're essentially swapping this alkyl group with the double bond for the carbonyl. So there are 2 carbons here. So we're going to add 2 carbons, and the carbon that is attached to the phosphorus will be double bonded now to the carbon that used to be part of the carbonyl. Although not shown here, the byproduct of this reaction is triphenylphosphine oxide. In the next reaction, either an organolithium or Grignard will add an ethyl group to this carbon and turn that ketone into a tertiary alcohol. And it will have 2 carbons, so an ethyl group attached to it. In the last reaction, chromic acid will oxidize an aldehyde into a carboxylic acid. Note that chromic acid will do the same thing with a primary alcohol. It will oxidize it first to this aldehyde and then oxidize it into the carboxylic acid. This first reaction, we're going to take an alpha beta unsaturated carbonyl and we're going to add hydrogen cyanide plus a catalytic amount of potassium cyanide. In the next reaction, we'll take the same alpha beta unsaturated carbonyl and add a Gilman reagent. Next, we're going to use the same alpha beta unsaturated carbonyl and add a Grignard or organolithium. And then lastly, a thiol will add to this alpha beta unsaturated carbonyl. First example, we have cyanide as a nucleophile. Cyanide usually adds to the beta carbon of an alpha beta unsaturated carbonyl, and so you'll get this as a product. Note that if we didn't have that double bond there, the cyanide would instead add to the carbonyl carbon to get a cyanohydrin. A Gilman reagent is considered a moderate nucleophile, so it generally adds to the beta carbon of an alpha beta unsaturated carbonyl. So in this case, this ethyl group of the Gilman reagent is transferred to that carbon. If we use an organolithium or a Grignard, we will transfer the alkyl group, in this case the ethyl group, directly to the carbon of the carbonyl to get a tertiary alcohol, as shown here. Thiols are considered moderate nucleophiles, so they generally add to the beta carbon of an alpha beta unsaturated carbonyl. Look at this synthesis problem. We're starting with an alpha beta unsaturated aldehyde, and we want to finish this synthesis with making this ketone here. With alpha beta unsaturated carbonyls like this aldehyde here, we can do additions of nucleophiles to both the beta and directly to the carbonyl carbon. So if we use a Gilman reagent that has 3 carbons, we can add that propyl group to the beta carbon. That will result in this aldehyde that now has 1, 2, 3, 4, 5, and 6 carbons. Notice in our product that we want to get to, we have a ketone that has 1, 2, 3, 4, 5, 6 carbons. So essentially, we now need to add these 2 extra carbons to this aldehyde. We can do that by adding an organolithium or a Grignard that has an ethyl group on it. That would lead to producing this alcohol, the secondary alcohol. which if we oxidize with PCC or chromic acid, we can turn it into the ketone that we're looking at here at the end of the reaction.